Again, welcome to Unit 2, Part 1 lectures. These lectures will be based on graphs and also trees. And the topic here is on discrete mathematics. And this is the course ITC 0341, Application of Discrete Maths and Statistics. So our agenda today is to go through the concept of a graphs. For example, what is a vertex or node? Edges, adjacents, incidence. Degree, we have two types, in degree and out degree. Then we will explain the difference between the two. Also subgraphs, adjacent matrix, undirected graphs, and also directed graphs, which we call the dark graphs. So first we start the use of graph theory in CS computer science, or the use of graph theory in information technology and computer science. The concept of graphs can be used in a car navigation system. Actually, when you take a course, a data structure, we have a graph data structure. The same concept here, but here we are focusing on the mathematics part of it. So in computer science, efficient database system, you can use a graph structure, or building a bot to retrieve info of www. Also representing computational models and many other applications such as GPS. Also, you can use the graph structures. So a graph in its intuitive notion, we have a definition here. So generally, a graph is a bunch of vertices, or we can call it nodes. And this can be represented as a circles. And we have to connect these vertices or nodes together using what we call the edges. So example of a graph here, we have two nodes or vertex with one edge. So a graph consists of two things, the vertex and the edge. So example of trees, this is a very important type of graph in CS, computer science, we call the trees. This is a real tree. A real tree, normally the root is at the bottom. And then we can do a transformation by having a vertex or a node on each section of the tree. It can be any random sections. Then we connect with edges. And this becomes what we call the abstract tree. Now the root will be at the top, and the leaves will be at the down. So a leaves is a vertex with no children. So let's assume this is our root. Root normally had vertices with no parents. And we go down. So there are different purposes require different types of graphs. Example here, we can have a bidirectional. A bidirectional means undirected graph. We can also have a directional, which is directed graph. So example here is undirected graph. And as we said earlier, a graph consists of vertex. So our vertex is 1, 2, 3, 4. We have 4 vertices. And the lines are the edges that connect the vertex. So we can see the first, we have 1 to 2, which means we are moving from 1 to 2. So 1 and 2, edge here will be 1 and 2. Also, you can go from 2 to 1, because this is undirected. So 2 to 4, 4 to 2, or 2 to 3, 3 to 2, or 1 to 4, or 4 to 1, then 3 to 1, or 1 to 3. So the edge is, the name of the edge here is just the two vertices that connect the edge. The edge that connect the two vertices, 2, 3, or 1, 2. So we say vertices are labeled to associate with a particular computers. And each edge can be viewed as a set of 2 endpoints. So a simple graph normally will represent by G consists of the vertex V and the edges E. Here we say consists of non-empty set of V. So which means we have to have at least one vertex, mostly 2 vertices, because one vertex, we don't have no edge, or we can have what we call the loop. The edge will go back to the same vertex. So a simple graph G equal to V and E, which consists of V, vertex, and edges. And the edges have to be non-empty set of vertices. So we have to have some vertex or node. And then a set of E, possible empty, is possible of edges. So for a set V with n element, how many possible edges there? So if I have a set of V, let's say we have n elements or n vertices, how many possible edges are there? So here we say the number of pairs in V, we have combination n and 2. So it will be n times n minus 1 over 2. The goal here is that, for example, if I have 2 vertices, I may have possible of 1 edge. We can have more than 1 edge, but the possible number of edge should be 1. So if I have 3, then it should be connecting one to the other, then connecting other, so it should be 4, etc. Then keep going. So how many possible graphs are there for a same set of vertices? So here we say the number of subsets in the set of possible edges. We have the smallest like average, n times n minus 1 divided by 2. Possible edges. Therefore, the number of graphs will be, again, 2 raised to the power of n times n minus 1 over 2. So it will be 2 raised to the power n. Because, again, we have one vertex, the edge, there's 2 possible vertices have to connect the minimum. So we have something we call the multigraphs. So if computers are connected through internet instead of directly, we may have different routes. And this is the concept of multigraphs. So different routes to choose from for each connection. Now, depending on the graph or the traffic, one route can be better than another. This is in terms of internet connection. So maybe one route will be short, one route may be longer. This makes sense to allow multiple edges, but still no self-loops. So this is an example for multigraphs. Here again, we have 4 vertices, but we can see that from 1 to 2, we have 2 edges. 2 to 3, we also have 2 edges. And from 1 to 3, we have 1 edge. From 1 to 2, we also have 1 edge. 4 is by itself. So based on this, we can label that each label edge, the edge labels will distinguish between the edges sharing the same endpoint. So for example, E1 will be 1 to 2. E2 also will be 1 to 2. E4 will be 2 to 3. E5 will be 2 to 3. E6 will be 1 to 2. E3 will be 1 to 3. So we say the edge labels distinguish between the edges sharing the same endpoints. Labeling can be thought of as a function. So a multigraph G consists of what? The vertex, the edge, and also a function in the labeling process. So this will consist of an empty set of V of vertices or nodes. A set E possible can be empty of edges, and a function V with a domain E and codomain the set of pairs in V. As we see in the earlier slides, the concept of V will say that each labels the series between edges, but labeling can be also thought of as a function. So E2, 1 and 2 can be a function. E5, 2 and 3 is a function. So we also have what we call a self-loop. A self-loop means the edge will go from 2 and back to 2 again, like E7 from 4 to 4. So labeling this, we have 4, 4, or just only 4. So let's label this again. We have E1 will be 1 to 2, E2 will be 1 to 2, but now we may have year 6. Year 6 will be 2 because it's a loop. And year 5 also is a 2 because it's a loop. Year 7 is 4 because it's a loop. Now year 4 will be 2 to 3. Year 5 also is a loop, so 2. Now vertices are adjacent. We say vertices are adjacent, that they are close together if they are in the endpoint of the same edge. So from 1 to 2, this is adjacent vertex 1 and 2. But 1 and 4, they are not adjacent because they are not close to each other. But 1 and 2, 1 and 3, they are adjacent. 3 and 2 also is adjacent because we have the endpoint. Now the question is, which vertices are adjacent to 1? The vertices that they are adjacent to 1 will be 2 and 3 because we have 1 to 2, we have 1 to 3. How about adjacent to 2? 2 will also be 1 and 3 because we have 2, 3, 2, 1. 3 also the same thing, 1 and 2 because 3, 1, 3, 2. And 4 does not have any adjacent vertex. So we say 4 is not adjacent to any vertex. But we can say the 1 and 2 and 3. 1 is 2, 3, 2 is 1, 3, 3 is 1, 2. So also so adjacent means the two vertices are sharing the same edge, their endpoints. Adjacent. Now a vertex is incident if or with an edge, and the edge is incident with the vertex if it is the same endpoint of the edge. So here we say which edges are incident to 1. How about incident to 2, 3, and 4? So we can say that here we have the edges year 1, year 2, year 3, year 4, year 5, year 6. So we can say here 1 is to year 1, year 2, and also year 3, and also year 6. So year 1, year 2, year 3, year 6 are incident with 2. Now, if I look at 3, 3 is incident, 3 is here, so it's incident to year 3, year 4, year 5, but not year 1, year 2. So incident basically means where the edge is connected. So they say a vertex is incident with an edge, and the edge is incident with the vertex if it is the endpoint of the edge. So which edges are incident to 1? I'll be 1 here. So okay, the edges are year 1, year 2, and year 3, and also year 6. How about 2? 2 will be year 1, year 2, year 3, year 4, and year 6. Actually, including year 5, sorry. So year 1, year 2, year 3, year 4, year 5, year 6. And 3 will be year 4, year 5, year 3. 4 doesn't have any edge. Also, we have what we call the digraphs. Digraphs is called a directed graph. So we have now we have arrow. Previous graph is undirected. Now we can see if I have arrow here now, I cannot say 2, 1 because it's going from 1 to 2. The arrow pointing to 4, so it will be 1 to 4. The arrow pointing back to 1, so it will be 1, 1. The arrow points this edge back to 2, so 2, 2. And 3, 3. And this straight one is again 1 to 3. So the direction of the arrow is where you end the vertex, 1 to 3, not 3 to 1. If we say 3 to 1 means the arrow is pointing to 1. So here they say, what type of pair should each edge be multiple edges not allowed? Now, we will go through that the second. Let's see this first. Each edge is directed so an ordered pair or tuple rather than unordered pair. So you can see here, I can't write 2, 1 because it's 1 to 2. Here now, I don't write only 1. On directed graph, we always write 1, but on directed, I have to say going from 1 to 1, going from 3 to 3, going from 4 to. Now, the previous question was asking, which type of pair should each edge be multiple edges not allowed? And my answer will be none, because multiple edges not allowed means I can have a vertex with no two or more edges. So the answer say each edge is directly so another pair or top rather than another pair. So the set of edges is just the representation relation on V, which is the vertex. Here, the only thing I want us to know is the direction of the arrow. This is a directed graph. So if I'm moving from 1 to 2, 2 to 3, 2 to 2, looping 3 to 3, that means it starts from the same vertex and end at the same vertex. So a directed graph or digraph, which consists of vertex and edges, must have a non-empty set of vertices, as we said earlier, for simple graphs or node, and also a set of E of edges with the edges belonging to at least two vertices. The edge have to connect to two vertices. So the edge AB is also denoted by A directed to B, because AB means I'm starting from A, I'll end at B, so A to B. And this is called the source of the edge. A will be the source, the beginning, and then the B will call the target of the edge, where we're going to end at. So A source, or I would say beginning, and then B is end, the destination or target. So the same as the number of relation on V, which is the number of subsets of V. So the same concept, V times so 2 to the power n times n. And we have an example of a directed graph. Yeah, so here we can come up with possible edges. So here, for example, we have 1 to 2 twice. So edge 1 and 2 is 1 to 2, 1 to 2. This will give me 2 to 2, 3 to 3, 3 to 3, 2 to 3, 2 to 3. The reason why it's 2 to 3 because I'm moving from 2 to 3. The direction of the arrow goes to 3. And that's what we have the edges. So 1 to 2, 1 to 2, 2 to 2, 2 to 3, from 2 to 3, 4. 5 also 2 to 3. E6 and E7 is the same, 3, 3, 3, 3. 2 loops in vertex 3. Now, next thing we're going to talk about, this is one of the questions in, I think it's question number 1B or something. What is the degree of the vertex? Now, the degree of the vertex is always the number of edges that are connected to the vertex. This is one of our questions in Unit 2 IP assignment. I think question number 2 or 3, I forget the question number. We also talk about matrix video already, which cover one of the questions also. So the degree of a vertex counts the number of edges that seem to be sticking out if you look under the magnified glass. So the degree of 1 will be 3. And this is undirected graph, so we have to be careful. Now, when we have a directed graph, we can have something they call in degree, out degree. In degree means the arrow goes there, out degree means the arrows come out. So the degree of a vertex counts the number of edges that seem to be sticking out if you look under the magnified glass. So this example here, I can count how many we have. This is 7, Y7, 1, 2, 3, 4, 5, 6, 7. And loop is a 2. So watch out the question. I think the question, one of the edge have a loop. So you should know counting. So for example, in vertex 1, the degree is 3. There's no loop. Vertex 2, we have 3 directions, 3 straight lines, E1, E2, E4. E6 and E5, they are loops, so they are 2, 2. So loop is 2, E5 is 2, E6 is 2, and E1, E2, E4 are 1s. So again, give a 7. And that's what they explain here. 1 plus 1 plus 1, which is E1, E2, E4. Then E6 is 2, E5 is 2. So the total will be 7. So now when you are dealing with undirected, so the previous was undirected graph. When we are dealing with undirected graph, we look for only the degree. And I think our question in the assignment also is undirected graph. Now, when we are dealing with directed graph, then we have in degree and out degree. So in degree of a vertex count the number of edges that stick into the vertex. In this case, the arrow goes in, so that is the in degree. The arrows come out, there's no arrow here, so that will be the half degree. The in degree represent negative, the positive. So this question is given, what are in degrees and out degree of all the vertices? So when I start with 1, I'll say the 1, the in degree is 0. We don't have any arrow coming to 1, so it's 0. But the out degree is 2 because we have 2 edges going to. Then when we look at vertex 3, the in degree will be 1, 2, 3, and 4. The looping. Then out degree will be 1 and 1 looping. So let's see the answers here. And the diagram is the same thing here. So we can see the in degree for vertex 1 is 0. There's no any arrow coming. In degree for vertex 2 is 3. 1 arrow, 2 arrow, and then loop 1 arrow, so it's 3. In degree for vertex 3 is 4. Why? Because we have 1 arrow, 2 arrow, the in 1 and 2, so 4. Now the out degree for vertex 1 is 2. We can see out, 2 point. Then out degree for vertex 2, let's look for out, 1, 2. Looping always is 1 out, 1 in, so 1, 2, 3. And the last out to be 1 and 2 is 2 loops, so 1, 1, 2. Then we have an example of handshaking theorem. This concept is the same as the previous slide, counting the degree of each vertex. Adjacency matrix, I made a video on it already, but let's see this example also. Here we have, this is our graph, a directed graph now. We want to come up with the adjacent matrix. Adjacent matrix means we have to represent the graph as a matrix. Now we have 4 vertices, so the graph, the matrix size will be 4 by 4. The graph again have 4 vertices. So 4 vertices means the matrix will be 4 by 4. So we start with 1. If I'm in the 1 position, I'll be in the first row. Then I'll say, okay, from 1 to 1, oh, I have 1 loop, so I represent it by 1. Now from 1 to 2, 2 is the column 2 will be the vertex 2. So from 1 to 2, okay, I still have 1 going, so 1. Then I'm still in the first row because I'm still in the first vertex. So from 1 to 3 is also 1. And the last one, I'm still at 1, and 1 to 4 is also 1. Now, when I go to the second row, I'm going to start at vertex 2. Second row, first column means 2 to 1. 2 to 1, there's no any arrow. Again, if it's undirected, I'll still have 1. But since this is directed, we have to use the in degree. We are using the in degree. So 2 to 1, there's nothing. So it's 0. 2 to 2, luckily we have a loop here again, so we have 1. 2 to 3, we have 1 also. 2 to 4, we have 1, the arrow going. Then we go to the third row. Now, when we go to the third row, we have to be at the vertex 3. So in vertex 3, it's okay. 3 to 1, there's nothing, so it's 0. 3 to 2, there's nothing. It's out, not in, so it's 0 again. 3 to 3, yeah, we have 1 loop, so we have 1. 3 to 4, we have 1, so 1. And the last one, we stand at the vertex number 4. We have 4. And then 4 to 1, there's nothing, 0. 4 to 2, there's nothing, 0. 4 to 3, there's nothing. And the last one, we have a loop, so we have 1. 4 to 4 is 1. So again, this is how we construct the adjacency matrix again. And that's the concept explained here. And the same concept explained here, the rows and columns. So anywhere you stand, the vertex that you stand at, that will be the row. Then you move it to first row, first column, first row, second column. First row, second column means you are moving from vertex 1 to vertex 2. Now, if you are using A, B, C, D, it's the same thing. So I'll say A is my first row, B is my second row, C is my third row. Whatever symbol we use, we just have to know the first one is first row, second, etc. So there's a question given here, what is the adjacency matrix here again? Now, we are using only in degree. So 1 to 1 will be 0. 1 to 2 now will be 3. But we have 3 edges. And we keep going. Now 1 to 3, 0, there's nothing. 1 to 4, we have 1. Then we stand at the second row, 2. 2 to 1, there's nothing, 0. 2 to 2, we have 1. 2 to 3, we have 1, 2, 2. 2 to 4, nothing. Then you stand at third row and we keep going. And this is the solution here. So I'm going to end here. In this lectures, we talk about what is a graph and also the basic concept of trees. Now, this is a discrete mathematics. It's not a data structure class, so we don't talk about the implementation of the graph or trees and go more detail, but we just talk about the theory and also the few mathematics behind it. So again, thank you and wish everybody the best.